Well, students, in the last class, we have started our discussion on numerical differentiation. We have established three primitive finite difference formulas for the first order derivative of a continuously differentiable function. And also we have obtained the mathematical error involved in these formulas. Further, we have introduced the method of deriving the finite difference formulas using polynomial interpolations. Today, we will continue our discussion on developing finite difference methods using undetermined coefficients. If you recall, this method is not new to us because we have come across the method of undetermined coefficients while deriving quadrature formulas also. The idea is exactly the same. Suppose we seek the formula for the kth derivative of the function f at a point x that involves n plus 1 nodes x0, x1 up to xn, then we write this formula in a general form like this. Recall, this is also the same as we had in the quadrature formula. That is, we want the approximation of the kth derivative of f in the form w0 f of x0 plus w1 f of x1 and so on till wn f of xn, where wi's are the weights or the free variables that are to be obtained by imposing the condition that this formula is exact if f happens to be a polynomial of degree less than or equal to n, right? This idea is same as what we did with the quadrature formula. So let us illustrate this idea with a particular case of obtaining a finite difference method for the second derivative of the function f at a point x with nodes as x minus h, x and x plus h. Remember, if we have a set of nodes of this structure, generally such formulas are called central difference formulas. Therefore, we are trying to derive a central difference formula for f double dash of x with 3 node points. Similarly, if you have 5 node points, you can also derive a central difference formula for f dash, f double dash, and so on. But let us consider these 3 nodes and see how to derive the finite difference formula for f double dash of x. As we have decided, we would like to have our formula in this form, where I have plugged in the choices of x0, x1, and x2 in their appropriate places. And let us use the notation dh2 f of x for this formula. Here we have to now find w0, w1, and w2 in such a way that this formula will be exact for the polynomials of degree less than or equal to 2. That is, if f happens to be a polynomial of degree less than or equal to 2, then whatever value you get from your finite difference formula should be exactly equal to the value of f double dash of x. That is the idea. Again, instead of putting this condition, we can equivalently put the condition that the formula is exact for these 3 particular form of the polynomials. That is, if f of x is equal to 1 for all x, then the formula gives exact value of the f double dash of x. And similarly, if f of x equal to x, then also it gives exact value, and f of x is equal to x square, then also the finite difference formula is supposed to give the exact value for your double derivative of f, right? So you hope to get 3 equations by imposing these 3 conditions. And in our general form, we have 3 unknowns. Therefore, we have the hope to solve these 3 equations and get these 3 unknowns. That is the idea. Let us go ahead and put these 3 conditions and see how these 3 equations look like. Let us take the first case, that if f of x is identically equal to 1 for all x, then the above formula can be written as W0 plus W1 plus W2 is equal to f double dash of x, that is equal to 0. And therefore, this is our first equation to be solved. Let us go to impose the second condition, that f of x equal to x for all x. In this case, the finite difference formula expression is given by W0 x minus h plus W1 into x plus W2 into x plus h. On the other hand, f double dash of x will be 0. Therefore, we will equate this expression equal to 0. And now if you recall, in the first case, we got W0 plus W1 plus W2 is equal to 0, right? Let us use this equation into this. Note that you can write this as W0 plus W1 plus W2 into x plus W2 minus W0 into h equal to 0, right? Therefore, the first term will go to 0 if we use the first equation, and we will be left out with W2 minus W0 equal to 0. Therefore, this is our second equation. Let us go to impose the third condition on our finite difference formula, that is f of x equal to x squared for all x. And in this case, the finite difference formula takes the form W0 into x minus h the whole square plus W1 into x square plus W2 into x plus h the whole square. I'm just putting f of x equal to x square in these three terms, and that is how I'm getting this expression. And on the right hand side, what we have to put is the second derivative of the function f, which is nothing but 2, right? So that is what we have. And again, you can see that this equation can be rewritten in such a way that we can use the first equation and the second equation and reduce this to a form given by W0 plus W2 equal to 2 by h square. So you can do this simple calculation and see how it looks like. So summarizing all this, we have three equations by imposing three conditions, and these three equations are given by this. One can solve these three equations and get the weights W0, W1 and W2 as W0 equal to 1 by h square, W1 equal to minus 2 by h square, and W2 equal to 1 by h square. So go back to your general form of the finite difference formula, plug in all these values here and just simplify it, and you get finally the expression like this, which is the central difference formula for the second derivative of the function f evaluated at the point x. Similarly, if you want to derive the forward difference formula, what you have to put is you have to write the general form as W0 f of x plus W1 f of x plus h plus W2 f of x plus 2h. And again, you have to impose three conditions, that is f of x equal to 1, that gives you one equation, something like this, but maybe different. F of x equal to x, that gives you another equation in place of this. And f of x equal to x square you have to put, and that will give you another equation in the place of this equation. Therefore, like in the central difference case, you will also get three equations. Solve these three equations and get W0, W1 and W2. Substitute those values into this expression, and you can get the forward difference formula for f double dash of x. Now, if you want backward difference formula, then how you should choose x0, x1 and x2? Well, you have to choose x0 as x minus 2h. Therefore, you will have W0 f of x minus 2h. x1 is x minus h. Therefore, W1 f of x minus h plus W2 f of x. And that will lead to the backward difference formula for f double dash of x. How will you derive that? Again, the idea is exactly the same. You have to put f of x equal to 1, f of x equal to x, and f of x equal to x square into this expression now, and that will lead to 3 linear equations. You solve those 3 linear equations and get your weights W0, W1, and W2. I'll leave it to you to do all these exercises. Let us go ahead with our central difference formula and try to derive the mathematical error for this central difference formula. As I mentioned in the previous lecture, the general idea of deriving the mathematical error for not only the central difference, for any finite difference method, is that you expand the terms in Taylor form and substitute them into the formula. Here you can see that one can put Taylor expansion for f of x plus h. Similarly, one can put the Taylor expansion for f of x minus h. Well, there is no scope of putting Taylor formula for this, therefore you just leave it. When you expand f of x plus h and f of x minus h in Taylor expansion, you get this. Remember, don't try to fix the remainder term at this stage itself, because when you substitute these expressions into your formula, certain terms will get cancelled, and then you will have some terms which are leading in your expression. Now that leading terms have to be frozen as the truncation error in your Taylor formula. Now we don't know what are all the terms that will get cancelled when you go to put these Taylor expansions into your formula. Therefore, at the first step, you write the Taylor series for this and don't fix what is the remainder term here itself. Then what you do is you go substitute these Taylor expansions into your formula and see that there are certain terms which gets cancelled. For instance, when you substitute f of x plus h here and f of x minus h here, that can be rewritten like this. Now you can see that the way we have chosen W0, W1, and W2, your linear equation from where we have chosen these weights suggests that this term actually goes to 0. It means in this expression, all the terms involving f of x are getting cancelled. That is what is happening here. And similarly, you can also see that this term is also becoming 0, because if you see the way we have chosen W0, W1, and W2 suggests that W2 minus W0 is 0, right? Therefore, this term also becomes 0. In other words, when you substitute these two expressions, even the terms with f dash are getting cancelled. That is what we are seeing here. Now, who survives? Well, this term survives, because if you go back to the linear system from where we derive W0, W1, and W2, you can see that W0 plus W2 is 2 by h square. So this is 2 by h square, right? So that will tell you that the coefficient of f double dash is not equal to 0. In fact, it is 1. And you see, surprisingly, even this is becoming 0. That is why it's not a good idea to fix the third term as the remainder term, because that may get cancelled in your formula, right? And you may land up in a higher order truncation error, right? So therefore, don't fix the remainder term at this level. You just write it as a series, substitute into this, and see who are all getting cancelled. Here, this also got cancelled, but this is not equal to 0. Okay, therefore, go back and write the fourth order term as the remainder. So in this formula, we have seen that this is 0, this is 0, and this term becomes 1. This is again 0, and this is not equal to 0. Therefore, you write this fourth order term in your Taylor expansion as remainder, and then carry that as a remainder. Since you are carrying this as a remainder, it will involve two unknowns. say xi1 and xi2. If you recall in the Taylor formula, the reminders involve unknowns, right? And these unknowns are in this particular case lies between x minus h and x plus h. So that is how you have to derive your mathematical error. Well, you can clearly see that the mathematical error by definition is nothing but the exact value, which is f double dash of x minus the approximate value, which we have used the notation dh2 f of x, and that is given by minus h square by 24, right? Fourth derivative of f evaluated at xi1 plus fourth derivative of f evaluated at xi2, right? Well, one can leave the mathematical error expression at this stage, but you can also see that we can use intermediate value theorem on F4 and just write this expression in a rather compact way like this. Again, recall that we are using an exercise problem from chapter 1. I think this is the problem number 9 in our notes given for quiz 1. You can refer that. I think it's in the first chapter. That is mathematical preliminaries chapter, problem number 9. If you use, you can just write this expression in this compact way. You just check whether all the hypotheses of that problem are satisfied here, then you can apply. If not, you cannot, of course, apply. So this idea we have also used in some of our previous error formulas. So wherever there is a possibility of applying this intermediate value theorem, you have to apply and get this compact form. Otherwise, that part of the mark will be reduced. And this is the required mathematical error finally. Let us now see how to derive arithmetic error involved in a finite difference formula. Especially these are very useful when we go to solve ordinary differential equations. As we have always seen right from the beginning of this course, that arithmetic error is quite serious in handling any numerical method, especially on a computer, because of the presence of the floating point approximations. Therefore, one has to carefully understand the behavior of the arithmetic error in each method that we use in our computation. As we have done in the quadrature formula, the idea is more or less similar in deriving arithmetic error for finite difference method also. What you do is you are supposed to use the exact value of the function at the nodes in your formula, but assume that you are only provided with an approximate value of the function at the nodes, which is denoted by fi, whereas the exact value is f of xi, and thereby we have a error which is denoted by epsilon I. Since I'm going to derive the arithmetic error as an illustration for the central difference formula with 3 nodes, I have taken I is equal to 0, 1, and 2, where x naught is x minus h, x1 is x, and x2 is x plus h. If you recall, these are the node points we have taken for the central difference formula. Once we understand how to derive the arithmetic error for this particular formula, in fact, the same idea can be repeated for any other finite difference method also. Well, let us recall that the central difference formula is given by f of x plus h minus 2 into f of x plus f of x minus h divided by h square. We will just use the notation f of x2 minus 2 times f of x1 plus f of x0 divided by h square. Ideally, we should also assume that there are some floating point approximations in the value of h, x0, x1, and x2. But for the sake of simplicity, we will only assume that only the function values are approximately given, whereas the nodes and other parameters are handled exactly. So instead of using the exact value, we are using only the approximate values in our difference formula. That is, we have f2 minus 2 into f1 plus f0 divided by h square. We will use the notation dh2 bar of f of x here to denote that we have used only the approximate values of the function and obtained the value of the central difference formula evaluated at x. Here x is denoted by x1. Now, what is the total error? The total error is nothing but exact value minus the final value that we obtain, possibly from the computer. And what is this? This is given by this expression, right? Now, note that this can be written as f of x2 minus epsilon 2. That is your f2 minus 2 times f of x1 minus epsilon 1 plus f of x0 plus epsilon 0, right? Divided by h square. Now that I can just separate these terms, f of x2 minus 2 times f of x1 plus f of x0, that I will keep separately and bring all the epsilon terms separately and write as epsilon 2 minus 2 epsilon 1 plus epsilon 0 by h square. Now you see, what is this? This is nothing but the mathematical error, and this is the expression for the arithmetic error. So finally, if I ask you what is the expression for the arithmetic error, you simply have to obtain this. Well, I have directly written the total error here. If you want to get the arithmetic error alone, what you should do is, by definition, it is given by the approximate value obtained by using exact function values, that is this, minus the approximate value obtained by using the approximate function values, right? That is this. This is going to be f of x2 minus 2 f of x1 plus f of x0 divided by h square. I'm just giving you another way of deriving the arithmetic error, minus f2 minus 2 f1 plus f0 divided by h square, right? Now that can be written as f of x2 minus f2 minus 2 into f of x1 minus f1 plus f of x0 minus f0 divided by h square, and that will give you epsilon 2 minus 2 epsilon 1 plus epsilon 0 divided by h square, and that is what we have written here. What I did here is I just directly wrote the total error as the mathematical error plus the arithmetic error. Okay, now we know the expression for the mathematical error. We have just now derived it, and it is given by minus h square by 12 into fourth derivative of f evaluated at some unknown point psi plus this expression for the arithmetic error, right? So that is finally the total error involved in this computation. Well, if you are given epsilon 0, epsilon 1 and epsilon 2, then you can explicitly find the arithmetic error. However, mathematical error may not be obtained explicitly because of the presence of this unknown parameter psi. However, if we know the upper bound of fourth derivative of f in the interval in which we are interested in, then we can dominate this term by its upper bound. And similarly, if we know some kind of ranges for these errors, epsilon 0, epsilon 1 and epsilon 2, then we can also estimate the arithmetic error. Let us try to estimate the total error and see how it looks like. For that purpose, we will use the notation epsilon infinity to denote the maximum of mod epsilon 0, epsilon 1 and epsilon 2 then we can take the modulus on both sides of the total error, and we can see that the arithmetic error is less than or equal to 4 times epsilon infinity divided by h square, because I am just taking modulus and then doing this mod epsilon 2 plus 2 mod epsilon 1 plus mod epsilon naught, and replacing everybody by epsilon infinity, right? And that is how I got 4 times epsilon infinity here divided by h square. So we got this upper bound for the total error. We cannot consider this as our final estimate because we still have an unknown parameter involved in the upper bound. So how to eliminate that? As usual, you can just put its infinite norm and you can freeze it to get h square by 12 into f4 infinity plus 4 times epsilon infinity by h square. So if we know this number and if we know this number, then you can see that the upper bound is something like h square some constant times plus 4 times some other constant, say c, by h square. So it is something like h square plus 1 by h square kind of function, right? So when you take h tending to 0, you can see that the first term, which comes from the mathematical error, is tending to 0. And you can see that the second term, which is coming from the arithmetic error, is actually going to infinity, right? So that shows that even if you have a small error in your function value, which is very likely when you go to implement all these formulas on a computer, then you can see that if you go on decreasing the value of h, you may be hoping that you get better and better approximation for your derivative, but actually the presence of the floating point approximation will eventually make your approximation very bad. So that is the dangerous part of dealing with the numerical differentiation on a computer. So let us summarize the observations that we got from the upper bound of the total error involved in the central difference formula for f double dash. The error bound will initially get smaller and smaller as h decreases. So we are just going in the decreasing h value and seeing how this right hand side will behave. Well, I'm sorry, I should have put this as f4 infinity. Okay, just note this. And then if you keep on in decreasing the value of h at one critical value of h, this term will start dominating and then it will take you to actually infinity. So I'm just plotting the graph of this function h square plus 1 by h square. Roughly, this is how this right hand side is looking like. So you can see that you take any h, your upper bound is something like this, and then you keep on decreasing your h. To some extent, your upper bound is nicely decreasing and looking as if it is going to 0, and therefore your total error is looking like it is going to 0. But after the critical point, say h star, your right hand side actually start increasing and it eventually blows up. Remember, it's only the right hand side happens like that. It doesn't mean the actual total error should also blow up, but in practical situations, yes, the total error will also blow up. We will illustrate this through an example in the next lecture.